Modeling petroleum feedstocks for gasoline desulfurization using 21st century analytical methods. I am George Hoekstra. I'm an independent consultant in the refining industry, and my company sponsors multi-client research projects for refiners. All our projects are multi-client projects that involve experimental work like pilot plant testing, analytical testing, and field testing. They're not just paper studies. A mark of our projects is that we are always generating new data. Today we are focused on two streams in the refinery. They are called Fluid Catalytic Cracking gasoline, which goes to a desulfurizer, and Fluid Catalytic Cracking diesel. We are interested in the detailed composition of the FCC gasoline, but the diesel stream is important because we will adjust the distillation cut point to shift light diesel up into the gasoline or vice versa, which changes the heavy tail of the gasoline, which changes the yields and the properties of the gasoline and diesel, and that is all critically important today for optimizing any refinery with a cat cracker. We are going to talk about a specific project we did this year for a particular refinery. That refinery wanted to be able to calculate this hydrocarbon type distribution by carbon number for the gasoline as a function of the percent diesel moved up into or down from the tail of the gasoline. This is a spreadsheet we developed for them. Hydrocarbon type is in the columns of this table, carbon number in the rows. So for example, you see at the bottom of the first column, this gasoline contained 29.3 weight percent olefins total. When the spinner in the upper left is used to increase the percent diesel, all the numbers change. The distribution shifts toward heavier, higher sulfur, more aromatic gasoline. This refinery uses this spreadsheet in our process model to calculate the detailed composition of the gasoline to optimize the economics of Tier 3 gasoline production, which is a smart thing to be doing these days. The sulfur type distribution is the other thing we need to know in order to do that modeling correctly. The sulfur distribution affects the difficulty of desulfurizing the gasoline. So we developed the capability to know that as the percent diesel is changed. So for example, here we have a light gasoline with 239 ppm total sulfur, and you see most of that is thiophenes. When the percent diesel is increased, the gasoline sulfur increases, and we get benzothiophene and sometimes even dibenzothiophene in the gasoline. And finally, this refinery has two primary feeds to their cat cracker, low sulfur and high sulfur feed. They want to be able to do this for both the high and low sulfur feeds. What I have just described is what we call feedstock modeling. It is the ability to accurately know the detailed composition of the gasoline over the full range of expected feed variables. And that's what this project was about. Now I'm going to back up for a minute and discuss the business case for doing work like this. Why are we interested in optimizing gasoline desulfurizers today? So stick with me for a few minutes while I cover several points on the business case. The first point is gasoline sulfur must be reduced to 10 ppm in North America by 2020. Here we see starting from 31 ppm in 2011, the annual average sulfur in the U.S. gasoline pool crept down very slowly to 18 ppm in 2019, which is the last year for which we have data. In 2020, for the first time, all suppliers to the U.S. market were required to make 10 ppm sulfur maximum, but that was easy because refineries were running at half speed in 2020. So 2021 is the first year when 10 ppm is required for all refiners while running near capacity. My company did a lot of work on this because we and some of my clients knew that reducing the U.S. gasoline pool to 10 ppm sulfur was more difficult and costly than one would expect from the amount of attention this critical sulfur specification was receiving in the industry, which is near zero attention has been getting paid to this critical gasoline sulfur specification that is now upon us. In the United States, 98% of gasoline sulfur comes from one stream, and that is the FCC gasoline we are talking about. We must now desulfurize that stream to remove 99% of the sulfur it typically contains. So now we turn our attention to the FCC gasoline desulfurization process. The FCC gasoline is desulfurized in a hydrotreating reactor that runs at mild conditions. It is a simple process, a low-pressure naphtha hydrotreater. The tricky part is the FCC gasoline contains 30% olefins, which are very reactive even at mild conditions. So when you desulfurize the stream, you also cause olefin saturation. Here you see an olefins by carbon number distribution for an FCC gasoline before desulfurization and after desulfurization. In this case, about half the olefins have been converted to paraffins in the desulfurizer. Why is olefin saturation a concern? Because olefins have octane near 100 and paraffins have octane more like 40. So olefin saturation destroys octane. And this is the chart the refinery really wants to know and control. And we will look at the solid black curve. It shows delta ron octane as a function of the desulfurized product sulfur. So we look at this chart from right to left. As we move from right to left, we are increasing desulfurization severity to remove more sulfur. The product sulfur is going down, olefins are being saturated, and the product octane goes down. The solid black curve shows that in this desulfurizer, the octane loss at 10 ppm product went down by 7 ron octane. Refiners want to move this curve up. The other curves on the chart show what can be done by taking steps to reduce octane destruction. So we call this chart the performance curve because it defines in one diagram the economic performance of the desulfurizer. You want to get sulfur out with minimum octane loss. And octane values keep rising. This is the difference in premium minus regular pump price differential at retail average for the United States. For decades, that differential was below 20 cents per gallon. Then it started rising and it has not stopped. The street value of octane today is higher than ever. Refining profits are being hurt badly by octane destruction that is occurring now in refineries in the U.S. for the first time because of the Tier 3 gasoline specification. And that is true even though you're not hearing about it in the industry headlines or from the refiners. It is happening. So I hope you stuck with me on that. Here's a summary of the business case. Gasoline must be desulfurized to less than 10 ppm sulfur for Tier 3. 98% of gasoline sulfur comes from FCC gasoline. Desulfurizing FCC gasoline causes olefin saturation, which destroys octane, which is costly and is hurting refining profits badly today, even though you are not hearing much about that in the industry, except for me. Now the rest of my time will be on a specific project we did for a refinery on feedstock modeling for gasoline desulfurization. This refinery wisely wanted to be able to model and optimize the feed to its gasoline desulfurizer because they knew the performance curve depends strongly on the detailed composition of the feed, and that is a high leverage point for their refining margin. We analyzed 4 samples from the refinery. They were the FCC gasoline and FCC diesel, sampled while running on 100% low sulfur FCC feed, and 2 months later on 100% high sulfur crude. We did 21st century analyses on those 4 samples. Several laboratories were involved. The FCC gasoline was analyzed by ASTM D6730 DHA, the 100-meter column version, which is run by Intertek, which is the standard test we run on all FCC gasolines, and we call it the blood test. We ran ASTM D8369 verified hydrocarbon analysis. That was done by VUV Analytics using their vacuum ultraviolet ASTM method. ASTM D5623 sulfur speciation was run by WR Grace, and Haldor ran for us their proprietary sulfur speciation for gasoline, which is used in connection with their licensed gasoline desulfurization process. On the diesel samples, we ran ASTM D8368 hydrocarbon type analysis for diesel by VUV Analytics. We ran a proprietary sulfur speciation method for diesel at C Solutions Limited in Thessaloniki, Greece, and we applied a proprietary method for measuring hydrocarbon type distributions in diesel. It is a two-dimensional GC method which I have access to. So let's look at some of this data. Here is an excerpt from the VUV Verified Hydrocarbon Analysis Report giving concentrations of individual hydrocarbons at the molecular level in the Dragon software format familiar to those who do detailed hydrocarbon analysis. The VUV Verified Hydrocarbon Analysis quantified 358 peaks in this FCC gasoline, and our performance curve spreadsheet model uses this full molecular detail as input. This is the output from W.R. Grace of sulfur speciation for gasoline by the standard ASTM method. This chart is from the Halder-Topsoe sulfur speciation method for gasoline. It quantifies sulfur compounds in greater detail than the standard ASTM method. Here is the sulfur speciation for a diesel sample run by C Solutions. I have used this method for 20 years now for catalyst testing and modeling of diesel desulfurizers. For this project, we are interested in the light part of the chromatogram, which quantifies the sulfur compounds that get lifted into gasoline when the gasoline's endpoint is extended. And this shows hydrocarbon type distributions from multi-dimensional GC analysis of FCC diesel. That was used to help quantify the hydrocarbon type distribution of the light diesel that gets lifted into the heavy tail of gasoline when the gasoline endpoint is extended. Putting this all together enabled us to deliver this spreadsheet, which enables the refinery to calculate the hydrocarbon and sulfur distributions for gasoline over the full range of expected feed and gasoline diesel cut points that they expect to see. Here is an example of some output from the feedstock model. First, for a light gasoline, you see on the top a narrow distribution of light aromatics by carbon number, and on the bottom is the sulfur distribution. The yellow bar shows 228 ppm of thiophene sulfur in a gasoline with total sulfur shown by the gold bar of 273 ppm. And now for a heavy gasoline from the same FCC feed, the gasoline now has a tail rich in higher molecular weight aromatics, and the sulfur has increased to 513 ppm with 346 ppm of benzothiophene. These two feeds have very different performance curves and very different Tier 3 gasoline production economics. We have done work like this in connection with field tests on 16 different commercial gasoline desulfurizers. Our clients are using our database and our models to optimize Tier 3 gasoline production strategy, optimize feed selection, optimize unit operation including endpoint cutting, optimize catalyst selection, evaluate investment options, design new units, and optimize sulfur credit strategy. Modern tools shine the light on octane destruction and gasoline desulfurization. I believe all refineries who make Tier 3 gasoline should have the data and tools we developed in our 3-year research program, including this performance curve model and the analytical methods that we call the blood tests. Actual commercial practice is far behind the available technology for this gasoline desulfurization process. When you shine a light on what is happening in your unit, improvements can almost always be achieved quickly and often with no capital investment. Everything we have done on this is available to anyone immediately for negligible cost. It is all multi-client, nothing is proprietary. All the pilot plant data, field test data, and modeling tools are available in the form of annual reports that include everything we did in a 3-year, $1 million research project. Plus, we are constantly expanding our database as we add new clients. So anyone interested in using this, please leave your business card and I will send you a link to our blog page and offer letter, or contact me anytime. I want to thank these 4 great companies for participating: VUV Analytics, Grace, C Solutions, and Halder Topsoe. And thanks a lot for your attention.